Hello, this is Miss Moore, and today during chemistry, we're going to start our discussion on stoichiometry. Specifically today, we're going to talk about mole-mole conversions. Today's essential question: given the number of moles of reactant used, how do you calculate the number of moles of products? Okay, today you will need your calculators handy. All right, here we go. Let's do a quick review on chemical reactions because chemical reactions are essential for stoichiometry. So remember that a chemical reaction involves changing substances. Okay, so you start with one or more substances, which we call the reactants, right? And they change into one or more new substances called the products. So the reactants, the bonds are broken, and then molecules or atoms are rearranged and form new substances called products. And an equation is what we use to describe the rearranging of atoms and bonds to make new substances. So for example, H2 plus O2 producing H2O, which means, and we need a 2 here and a 2 here. Okay, so this that I wrote down is the equation. The reaction is the process of hydrogen molecules and oxygen molecules getting together and making a water molecule. So this is how stoichiometry and reactions go together. So stoichiometry is a method in chemistry that uses a balanced chemical equation to predict, important, we're going to predict the exact amount of a product produced. If you know how much reactants you started with, you should be able to predict how much product you'll make. Or if you know how much product you need, you can figure out how much reactants are needed to produce that amount of product. Okay, so that's what we're going to be working on for the rest of this unit, predicting the amount of reactant needed or product produced in a reaction. All right, let's get to the stoichiometry. So first, stoichiometry conversion factors. Hopefully you remember when we did mole conversions, we had the conversion factors or the equalities. 1 mole equals 6.022 times 10 to the 23rd atoms or molecules, or actually anything. And 1 mole of something equals the molar mass of something. Right? Those were the conversion factors. Well, we're going to learn a few new conversion factors for this unit. So I'm going to give you all of them now, although today we're only going to focus on one of them. So the first one is what we call mole-mole ratio. And I'll explain how to get the mole-mole ratio in a little bit, but the actual equality is mole known equals mole unknown. Okay. And then the next one, and this looks very similar to one we've already used. We have 1 mole of known. 1 mole of known equals the molar mass of known in grams. So that one is just like this guy up here. 1 mole equals molar mass of something in grams. But this time I'm specifically giving you the word known. And then we have the third one is 1 mole of the unknown equals the molar mass of the unknown in grams. And again, that one is just like the one we used in the mole unit. 1 mole equals molar mass. The difference is I'm specifying the unknown. And why I'm specifying known and unknown will become clear as the unit proceeds. All right, let's get to mole-mole conversions. So for mole-mole conversions, the first thing we need to talk about is, let me go back here real quick. this mole-mole ratio thing, this guy right here. What is that mole-mole ratio and how do we get it? So for mole-mole conversions, the coefficients in the equation show the number of moles of each molecule or element being used or created in a reaction. Remember the coefficients that we used in the reactions unit, the chemical reactions unit? We use those to balance the equation, right? So that we end up with the same number and types of atoms on both sides of the equation. So we're following the law of conservation of mass and matter, right? Well, it turns out that those numbers, what you could say is that we have 6 moles of oxygen and 6 moles of carbon dioxide and 6 moles of water. And this guy here, the first one, C6H12O6, has no number there. That doesn't mean we have none of them. Remember, there's an invisible 1 there. So we have 1 mole of C6H12O6. So the way you could think about this is for every 1 mole of C6H12O6 used, you make 6 moles of CO2. Or you could say, well, so we could write that down. So you could actually say 1 mole of C6H12O6 equals 6 mole of CO2, right? Because you need a mole of C6H12O6 to make 6 moles of CO2. You could further say that if you have 6 moles, or you need 6 moles of oxygen to make, let's say, 6 moles of water. Okay, and this is all mix and match. You could also say that if you need 1 mole of C6H12O6 to react with 6 moles of O2. Or you could say that when you make 6 moles of CO2, you also make 6 moles of H2O. Okay, so the coefficients are telling you how many moles, and there's a relationship between all of them. Okay, so we're going to use this for mole-mole conversions. So scroll up. So mole ratios can be used like conversion factors to compare amounts of substances, and we just talked about that. Find the coefficients, the numbers in front, or if there's no number, it means 1, with the units moles for the 2 atoms or molecules in the question. And then use the mole ratios as a conversion factor in the factor label method. So just like, we had 1 mole, equals 6.022 times 10 to the 23rd, like atoms or molecules, and we put that into the grid, we can now use something like, say we were interested in CO2 and H2O, we would say 6 moles, we'd use this right here, 6 moles of O2 equals, did I say CO2? Sorry, 6 moles of O2 equals 6 moles of H2O. And we would use this, we'd put this in the grid. It's just like using this one. The only difference is this will change for each type of reaction. And not only for each type of reaction, but also for molecules you are using. Okay, and if this seems weird, please don't stress too much. When we start doing the problems, you're going to see it's really not that big of a deal. You just need to be careful, just like we were with the mole unit. All right, let's go through the steps and do a couple practice problems. So the steps for completing mole-mole stoichiometry conversions. And the example we're going to use is how many moles of CO2 would be created from 3 moles of C6H12O6. And we have the same balanced equation. So the first step, I'm going to scroll up and I'll come back. The very first step is to set up the grid and write the given over 1. So same thing we've done in the past. So we'll set up our grid. And please wait for that. We're going to set up our grid. And we're going to write our given or our known. And our known is this guy, right? Because we know something about that. So we're going to write our known over 1. So we have 3 mole CO2. No, where did I get that from? Sorry. We have 3 mole C6H12O6 over 1. Okay, just like we've done in the past. All right, step 2 is also the same. So I'm going to scroll down a little bit. So our step 2 is we're going to use our conversion factor or equality to determine the mole-mole ratio. So that's the thing we learned recently, right? Our mole-mole ratio for the reactants and products you're interested in. This is important. You're going to have to go back and really look at the equation to see what we're interested in. And the mole-mole ratio is now going to be our equality, just like we were using 1 mole equals 6.022 times 10 to the 23rd, which we're not going to use this time, but same idea. And remember, this is important, the coefficients come from the balanced equation. All right, so we've got to first find what we're interested in, and then look at the balanced equation to find our equality. So let's go back and do that. So our known we already figured out was, we're interested in 3 moles C6H12O6. So let's find that in our balanced equation. It's right here. And then we're trying to find our unknown is moles of CO2, right? So let's find that in our balanced equation. Okay. And let's turn those into an equality. So we're going to have 1 mole, because of the invisible 1, of C6H12O6 equals 6 mole of CO2. Whoops. CO2. So again, I got these from the balanced equation. And what we do now, same as before, but let's look at it real quick. So put the conversion factor or equality into the grid. And what's important about that, you want to set it out so that our units cancel out. Although this time, it could be units, or I could say, or atoms, molecules. And I'll show you why I wrote that in just a second. All right, so let's go back to our problem. So we want to set this up. We want to put this guy in this area here, right? So we have the units mole in our problem, in our grid already. The problem is we have the units mole here and here. So we have to look at something more. We need to look at the atoms or molecules. So it's our mole of C6H12O6, right? Which makes it, we're going to be using that one. Let's get rid of all those underlines because it's going to make it confusing. So I'll put 1 mole of C6H12O6 on the bottom and 6 moles of CO2 on the top. And then our stupid mistake blocker, does this cross out? Does mole C6H12O6 cross out mole C6H12O6? Well, it does. the last thing we should do is look and see where we're at right now. We're at mole CO2, which is what we were looking for. So from here, all we have to do is multiply across the top, multiply across the bottom, and divide. So when I multiply across the top and bottom, I end up with 18 mole CO2 over 1. And when I divide, I end up with 18 mole CO2. And then the last step, everybody's favorite, sig figs. So we look at our problem. We have a 3 there, right? That's 1 sig fig. We don't use the numbers from the balanced equation, this area here, for sig figs. We only use, for today, our given, and if we use molar mass, because that's calculated as well. So we have 1 sig fig here, which means we're going to keep the 1. The 8 rounds the 1 up to a 2. And because we're dropping a number before a decimal, we're going to put a placeholder as a 0. So we have 20 moles CO2. And that's really all there is to it. It's not much different than mole conversions, just a little bit more thinking, and you need to be a little bit more careful. So we're going to try another practice problem. All right, let's try another practice problem. So using the equation below, how many moles of oxygen are required to react completely with 22.34 moles of aluminum metal? And then I gave you the equation down, the balanced equation down below. Now, if you think you might understand how to do this by watching the previous problem, hit pause. Try to do this without me, and then hit play and see how you did. All right, so first step is we're going to write our grid and write in our known. And our known is 22.34 moles of aluminum. Okay, so I'm going to put that in my grid, my known, 22.34 mole of aluminum, and that's over known. All right, step 2 is to find the things we're interested in, our known and our unknown, in the balanced equation. So we already know we're interested in aluminum, so we're interested in that. And then our unknown, let's see, we're looking for how many moles of oxygen. Okay, so this is our unknown, and this is our known. Okay, so going to our balanced equation, moles of oxygen right here. So our equality then is like this. 4 mole aluminum equals 3 more moles of oxygen. And again, that came directly from the balanced equation. And we need to put these in the grid, setting it up so that everything cancels out. And because we have mole AL here, we want mole AL at the bottom, which means we're going to use that one, is going to go on the bottom. So, and what's left goes on the top. And our stupid mistake blocker, let's check to make sure stuff cancels out. Mole AL indeed crosses out mole AL, and we're left at mole O2, which is what we were looking for. So now we need to multiply across the top. And if I did this right, I came up with 67.02 mole O2 at the top. And multiplying across the bottom, I ended up with 4. And then I'm going to divide those two, giving me 16.755 mole O2. And the last step, everybody's favorite, sig figs. So our given is 22.34 moles. We don't use these as sig figs from the balanced equation. So So we need, yes, 4 sig figs here. So 1, 2, 3, 4. This 5 rounds the 5 up to a 6. So final answer would be 16.76 moles of O2. Okay. That's really all there is to molar stoichiometry. It's not that hard, but you need to go back and forth. Look at the question. I highly suggest circling or highlighting or something the known and the unknown in different colors, and then do the same with the balanced equation. It will make setting up the grid really easily. And then, of course, watch those units. Write them, cancel them out, double check, double check. All right, that's it for today. Have a good one.